All right, everyone. Thank you for coming to this bootcamp. A lot of you might be unaware of the purpose of this bootcamp. This bootcamp is to help you people get started with the homework and also give you some tips about the homework and how to go about it. We will not be able to take specific doubts regarding in the implementation or code in this bootcamp, but you're welcome to come to the office hours and we'll be happy to help you. So we will get started with a brief introduction to the homework part one, and then part two. We'll spend more time on part two because I think we need to give like more information about part two this time. And you're expected to have gone through the homework handout and the starter code for this bootcamp to be more fruitful. If at any point you have any doubts about what I'm saying, you're free to interrupt and ask questions. So let's get started. Let me share my screen first. Share screen. And here. Do you guys see the handout? Yes, all right. Okay, so I cannot emphasize this enough. The handout for homework one, part one is your friend. Everything you need to know to complete this homework, part one, is in the handout. Even the concepts that have not been introduced in the class or recitations are kind of required to do this homework, but the handout is so detailed that you don't really need to know all of those. If you just go through the handout, and we've provided you with all the math, all the equations, and even those equations are solved. Even if you do not understand those equations right now, they have been solved for you and you just have to code them. And these concepts will soon be introduced in the upcoming lectures and slides, and professor will do a lot better job of like going into the details of everything. So the part one of the homework is where we write our own code for a mini library we called MyTorch, like our own version of PyTorch, and we can only use NumPy for this. You will be provided with a local autograder in this part, so you can run that and set the appropriate flags and know your score before you submit it to the autolab. And you can find the details for that in the scoring as well. Right, so this homework is very straightforward, very easy. Do you guys see my VS Code window? Can someone respond to that? Or do you still see the handout? I cannot see the chat, so if someone would unmute themselves and let me know. Okay.
Yeah, we can see it.
Okay, you can see the VS Code, right? Okay. So in this part, this is kind of like the file structure we have, and you will be implementing the modules we have in PyTorch. So basically activation, batch norm, linear loss, SGD, and then finally homework one. I think you can do activation first, linear and loss, and then you can go to homework one. I think HW1 will work without SGD and batch norm, but that's on your preference. I would recommend doing activation, linear, and loss first, and only then going to homework 1. So as I said, everything is super straightforward. You are given to-dos that you need to fill in for this. And 1 second. You are given to-dos that you're given for the homework, and these are basically one-liners. You don't have to like write, I don't know, a crazy for loop to do this. All of these things can be just done in one line of code, usually. And also, oftentimes you have to return whatever the function has to return. So for example, here you have to calculate the derivative of the loss with respect to the output, and then return here. So let's quickly look at activation, I guess. So for example, you're trying to code the sigmoid function. You have a class, and inside you have a forward function and a backward function. So the forward function will basically compute the forward pass, and the backward is the derivative of the sigmoid. And it's so simple that you don't even have to like do it by yourself. For example, you can just come to the activations part in the handout, and you can see that for each one of those, for example, sigmoid, it tells you what the forward of the sigmoid should be. The equation is here, you just have to code it. What the backward of the sigmoid is given to you, right? All the shapes and dimensions are given here, all the variable names and what they mean, the math notations, everything is given here in tables. You can read them and use them to debug your code. Even small tiny examples that are easy to work out by hand are given here, so you can go through them, and it should make your life a lot easier. Same goes for the tan or the ReLU as well. You can just look at the handout and it'll tell you what to code. And it's fairly simple to do the loss as well. Loss, so loss tells you how far away your output from the expected value is. And essentially what we're doing here in this homework is we're trying to find, like, the purpose of writing a neural network is to find the optimum weights that minimize the loss, right? So I know we haven't gone over this in the lectures, but professor will soon get to this thing we call gradient descent, and this thing we call backpropagation. If you've watched the first recitation, you should have a bit of an idea about what backpropagation is and what gradient descent is. And so that's what you'll be just doing. Hold on 1 second. Give me a second. Someone's. All right, sorry about that. Let's continue. So yeah, we were talking about backpropagation. So that's all we are doing in the backward of computing the forward pass is fairly easy, but backpropagation is what we're doing in the backward of each function that we write. So going back to the code. So we have modularized most of the code, and that should make your life a lot easier, I guess. Let me 1 second. Yeah. So that should make your life a lot easier. So one thing I wanted to go over was homework 1, MLP 0. I think, let me try to have it side by side so it's a lot easier to relate. 1 second, give me a second. All right. All right, can you guys see it side by side?
Yep.
All right, so yes, when you're about to do the homework 1 MLP 0, you're expected to have done activation, linear, and loss first, and then when you're doing MLP 0, you're basically writing the code for 1 layer MLP. So this, and for example, essentially what you're trying to do is in the forward pass, you're taking the input values, so A0, and you're computing A1. That's all you're doing in the forward pass. And in the backward pass, you're essentially calculating derivative of the loss with respect to A0. That's what you want. So DL by A0. So let's see how we would typically go about doing. So MLP is just a 1 layer MLP 0 is just a 1 layer hidden layer MLP, as you can see from this figure, and we have given the layers in just a list. So what you can do is, here in the forward pass, you get A0 from here, right? And you want to calculate A1. So how would you go about doing that? I think we can just go over it. So we can be like self dot layers of 0 dot let me, okay, I don't know why it's doing that, but anyways, so self dot layers dot 0 is linear of 2 comma 3, right? And then what we need to call the forward function from the linear. So here you're expected that you're already completed this, and you can just call the forward function of the linear and pass it is 0, right? So you get from A0 to you get from A0 to Z0 now, right? And then basically you've done the affine sum of the inputs, and now you want to pass it through activation function. What is our activation function? It's relu. So how do we go about doing that? At this point, you've already completed the activations module, and relu implemented the forward for the relu. So what you just have to do here is call self dot f of 0 dot forward, and you give it A1, and that's all you have to do for the forward. And then finally you return A1. Any doubts until this point? All right, let's move forward. So let's define the backward. So what we're doing in the backward is we're finding DL, derivative of the loss with respect to the input, DL by DA0. That's what we are returning here as well. So I don't think you have to return. You can just save it in DL A0. So let's see. We do not have a direct relationship between the output and A0. We have A1 and Z0 in between them, right? So what we can do is apply the chain rule to find derivative of the loss with respect to the inputs, which is DL by A0, DA0. So let's see how we can do that here. So what is DA1 by DC0? Does anyone want to take a shot at that?
Is it derivative of f function f?
Yes. So that's what Z0 is the affine sum and A1 is the output that we get after the applying the activation. So we just have to call the backward of the activation here. So self dot f of 0 dot backward, and that's it.
Actually, in the forward function, could you explain what do you mean by like A1 equals to like F0 forward A1? I'm a bit confused.
Oh, so F, what's F? F is ReLU, right? Like you, so this is MLP0, it's a one layer MLP. If you look at MLP1, you have two layers and two activations. So you'll be indexing that in that order, like this is the first layer and this is the second layer. So first you have to pass your Z0 into layers.0.forward, then activation.0.forward, and then layer one layers dot of one dot forward. So 0 is just indexing into the list of the activations.
But
I
like,
think there's a typo on line 18.
Line
I think that should
18.
be Z0.
yeah,
Oh,
it's
yeah.
like forwarding
Thank you for that.
A1, which yeah doesn't make sense. Yeah, thank you.
Yeah.
Z0.
Yeah, good catch. Right. So yeah. So we have DA1 by Z0, right? And we want to get here from here to D derivative of the loss with respect to A0, right? So going by the chain rule, we can go from D, we can get the derivative of the loss with respect to A1, right? Which is already given to us. We will get this from the loss function, but here you don't have to implement that. I think the autograder automatically sends in an input to check your function, but we get this from the backward of the loss that we've already implemented here. And so applying the chain rule, we get the derivative of the loss with respect to Z0 as DL A1 times DA1 DZ0. And we've already calculated DA1 DZ0 here. And that would give us DL DZ0. So derivative of the loss with respect to the affine sum at the first layer, right? And now we've reached at the layer, first layer. So we're gonna go from here to You want to go from here to the derivative of the loss at A0 at the input. And because this is a linear layer that we've already implemented the backward for that. So all we have to do is self dot what dot layers of 0 dot backward and DL DZ0. And that's about it. I don't think you need to do anything else in MLP 0. And so anyone who showed up at the bootcamp got MLP 0 for free. The same logic and everything will hold for MLP 1 and MLP 2. I'm not MLP 4 as well. It's just a couple more steps, like you go from layer 1 to activation 1, layer 2 to activation 2, layer 3 to activation 3, and so on. And same logic holds for the backward as well. So it should be fairly straightforward. Yeah. So again, everything, all the equations, all the backward are here in the handout. You can go through them. And professor will go into the details and the mechanics of backward propagation and gradient descent in the upcoming lectures. And the only challenging part you might find in this homework is batch norm. But you might find it challenging only because it hasn't been covered in the class yet. It will be covered soon. But again, all the equations and all the math have been already given to you. You just have to code it in. But yeah, if you have like specific doubts regarding that, just wait up and it'll show up in the lecture and professor will do a much better job of explaining that. Right. Any doubts at this point?
Any chance you can show us like how to use the autograder?
I think so. I think you just have to set the flags to true to whichever module you want to test, and then just make sure you're in this directory. Your directory should be autograde, I guess. Yeah, so you should be in the autograde directory. I think I'm not in the autograde directory right now. You have to be one layer up, and just run this command and it'll show you your score. Should be straightforward. You just have to be in the autograde directory, this one, and just run the autograder file.
Okay, thank you.
And yeah, set the flags here. Any more questions at this point? All right, then I'll hand it over to Royu and he will go over the part 2 of the homework. Let me stop sharing my screen. Yep.
Okay, let me share my screen. Can everyone see my screen now?
Yes.
Okay, great. So let me introduce the part 2 briefly. Please mind that we have an early submission deadline 9 days after today, and you should complete not only the homework 1 part 2 MCQ, which is the on the canvas now. And you also need to complete most of the code and then submit it to Kaggle. So there are two things that you should do before September 15. You need to log into your Canvas and complete MCQ questions, and you also need to complete your part 2 code and then submit to Kaggle. And the official on-time deadline is on September 29. So after that, you would use your Slack days. So we listed some very useful information in the write-up, so be sure to read this before you start. Also, we created a checklist for you, and we strongly recommend you to go over all the items, because if you check all the items in the checklist, you will be able to solve the most difficult parts, and it could help you to see which part is not making sense for you. Yeah, so this first homework 1 part 2 is a framework, is a frame level classification assignment of speech. So your input is some mouse spectrogram features that we already provided for you, and if you are interested in how we convert the audio files to these mouse spectrogram features, you could click the link we provided in our Piazza post. And for this homework, you could only use the fully connected network. So you could only use the linear layers, the activation functions, instead of using those the CNN or LSTM things. The input here is so in this example, we have 3 nodes, and these are the feature dimension. This is just a simple example, and output is of 2 dimension. It means maybe we have 2 labels here, and in each node we output the probability of node 1 and node 2, and at last you may want to choose the label with the the highest predicted probability, and use that as your output for this input. So I think you can read these things yourself. Let me just go directly to feature part. So our data looks like this. We provided the data like this. This MFCC is your input. It's those mass spectrogram input, and the transcript here is the label we provided for you. For train set and evaluation set, we provided the transcript, but for test set, we are asking you to predict the phonemes, predict the label based on the MFCC, your input. So you're supposed to train your model on this training set, and use just pass the MFCC the input to your model, and then use the transcript here, use the label to calculate the loss and do the backward propagation. Use the training set to update the parameter of your model, and then use this evaluation set to evaluate the performance of the model. Although we provided the labels of the evaluation set, we don't expect you to train on this evaluation set, because your your evaluation result will be more like will make more sense if you evaluate all a part of input that your model have ever seen before. And at last, you need to put the MFCC in the test set and then submit your predicted results to Kaggle so that we could generate the accuracy of your model and then calculate your final score. So if you already like, actually I can do that. Let me open the Kaggle page. So in the like the MFCC folder, in the input folder, we provided many these kind of MPY files. And if you read any of these files, it will be a two-dimensional vector, a two-dimensional tensor like this. And for the transcript folder, it has the same number of files as the MCC files because you want to because each input would have an output. So if you read the transcript file, like any of this transcript file here, it will be a single array, and their shape is related, like not exactly the same, and I would discuss that later. So you may notice that the shape of X is something, 15. So we illustrated like how what is the meaning of this first dimension. But for the second dimension, you can see that as the dimension of our feature. So if you are not interested in how it generates the first dimension, you actually this number, this 13 here has a little mistake. It should be 15. Should be 15. And if you're not interested in the first dimension, the generation method of the first dimension, you could just think that for an audio file, it has like several this kind of columns, this kind of vectors, and each of this vector is 15-dimensional vector. So so the final shape of this audio would be t, 15. And here I printed out the a Y example. So it started with a SOS and end with an EOS. For this homework, they are not being used. So when you write your data sets, you can just you can just use some tricks to delete these things. But for the middle parts, they are corresponding to the each vector. So this first SIL is the output of this first vector. The second SIL is the output of this second vector. So if you subtract 2 from 198, it will be 196. So you're basically subtracting the length of this SOS and EOS, and their first dimension will be the same. Okay. So this is just something about like the dimension thing. And so we introduced that like for each of this vector, it will corresponding to a like the prediction or a label, a phoneme label. But when you make the prediction, of course you can use this single vector as the input and let your model predict like the label here based on this single vector. But sometimes, but we also know that in order to understand a word, you may need to use some context information from like maybe several seconds before this vector and several seconds after this vector. So you may want to use some extra information we call context here, like to put several vectors before the current vector and several vectors after this current vector as the input, and use this whole thing together and pass it to the model to let the model make a more precise prediction. So let's assume that you set the context size to 3. So in this example, you want to give like the later 3 vectors and the former 3 like vectors together with the current vector as the input when you like both training, evaluating, and making the prediction, the inference. You want to pass this whole thing as the input and pass it to the model and make it like generate the prediction. In this case, your the dimension of your input will be 1 plus 2 times context size times 15, because 15 is the width of this feature. So the 1 here is just the centered vector, and the context size is related to your setting. This is the idea of concept of context. It's really important, so make sure you understand what we introduced in this part in the write-up, because it you cannot pass the low cutoff without using this context size. And for the evaluation, this is not the evaluations that we talked before. So we will release the cutoffs later, and we will also release a architecture suggestion to let you reach median cutoff later. So please focus on pay some attention to our PSA post, and then follow the instructions we provided, and remember to complete this 10 points of this mission. So the submission formats. So the submission format should include 2 columns, the ID and label. The ID is just a self-incremental ID from, I think, starting from 1 or 0, from 0 to this number. And this number is the total number of input vectors provided in our test set. Is the total number of all the files we provided in the, is the total number of the feature vector that we provided in the test set, right? So there's some other information in the write-up, so just look at this yourself, and let me move on to the starter notebook. So we suggest you to use this WMBE to log the training progress of the model, but feel free to use like anything else, or maybe just not using it. So the first part is, of course, importing some libraries we will use. And the device here is specifying which device you want the model to train on. So if you are training on a computer that support CUDA acceleration, you could enable it. But if you're just want to debug something like in a very early stage, you could just use the CPU, especially when you want to train on Colab. You might want to start with the CPU version first, because Colab will restrict the time you can use on the the GPU version machines. So you can change this yourself. And the phone list, I believe this one has the same content as the phoneme.txt we provided in the dataset. So for these two things, I think that they are not being used right now, so but we still provided it. For people who want to use some Colab for training, please remember to run this command to upgrade your Colab Kaggle version, because we have seen students like not running this and leads to some very strange dataset errors before. And to download the dataset from Kaggle, you could click on the account settings and generate the Kaggle API, and then fill in your username and key here. And after that, you can just run this download command, and it will allow you to download the dataset directly from Kaggle instead of copy paste your dataset from your machine. And remember to join the competition, because if you don't join it, it will give you some permission errors. Okay, so let's move on to the dataset part. So this one is the torch dataset is an abstract class provided in PyTorch, but you are expected to implement some key functions like this initialization function and the get item function of this abstract dataset class. So we provided some comments here. The MSCC directory is the directory for the input files, and the transcript is the label files. So you could just put your path here, and for the names you could use some Python APIs to get all the file names from your
Roy, so sorry to interrupt, but people want you to make the text bigger.
Oh, I'm sorry. How to let me see. No, it doesn't have. Okay, let me stop sharing and then switch to another version.
I think you could do command and plus to increase the font size.
Oh yeah. Great. Thank you. Okay, can everyone see the screen now? Okay.
Yep.
Okay. So for the MCC names and the transcript names here, you should pass the directory we defined earlier in these two lines, and then use some Python API to get all the use this API to get like all the file names under these two directory. And for here, you could use the numpy.load function to like this to load each input and the label file into memory and define it here. So after you read from the numpy file, you could just add it to the input array and output array, input array and label array here. And the next thing is how to preprocess the the input and the labels. So we introduced that each input file is of shape t, 15, but each transcript is of shape t plus 2. Is a t plus 2 dimensional vector. So here at first you want to remove this plus 2, the SOS and the EOS character from the label, and then here you might want to do some concatenation to concatenate over the first dimension, so that in the get item function here, when you pass an index, you get the corresponding input. So can I draw some? So this is an array. Let's assume that you're not using the context now, so the context size is 0. So the meaning of this get item function is it will pass an index. So when you call the enumerate data loader when you're training or doing the inference, the get item function will pass the index automatically. And for example, you start with the index 0, so it would so you should return the input at first position, and next time it would pass the index equals 1, and then you should return the input and the label of the second position. So think about how to how to generate your input, especially when the context size is used, because it would be a little different from the example here. Just use the index to return the the array in that position. So you might want to use some the NumPy padding or the slicing things to get the input frames. And for the output, you can just use the index to get. You can just use the index to get the label on that position. So I think that's for the data set. For the that's for the training set and evaluation set. And for the test set, because we are not providing the labels to you, because we want you to predict the labels yourself. You need to notice the difference between the training set and the test set. So in the test set, you don't have any you don't have anything related to the transcript, so you don't need this transcript directory. You don't need to get the transcript names. You don't need to iterate over the transcript and load it to your transcript array. So deleting all these things related to transcript should be fine in the test set. Is there any questions?
I ask a quick question?
Okay.
Yeah, I see that we're supposed to concatenate all of the MFCCs into a big list.
This one, right?
Doesn't that mess up? Yeah, doesn't that mess up the context? Like, let's say I have MFCC 3, the one that was originally 3, and it was length
Okay.
T3.
Yep.
And I take the last element, and there should be some context there. Shouldn't the context on one side be zeros instead of MFCC 4?
So yeah, so of course you need to think about how to implement the context without affecting the original input. So yeah.
So just to clarify, even though they're all concatenated into a huge list, you still, when you take the last element of number 3, you should get zeros instead of the first part of number 4?
Let me.
Can you ask your question again?
Sure. Yeah. So we've got, let's say we've got, I don't remember the number, we've got 100 MFCCs, right?
Right.
Yeah.
And they're each of length T1, T2, T3, T4.
Yeah.
And let's say you're supposed to take the last index of MFCC 3, and you got a context
Last
of, let's
index.
say 5.
No, so the MFCC is 15 dimensions long, and you will be passing all the 15 dimensions at one, not just one index.
But doesn't an utterance have a certain length?
I think let me use this graph to
I think each MFCC is 15 dimensional.
So for example, this is MFCC. Oh, this is not MFCC. This is the input 1, the input 2, input 3. Yeah, this is the input 2, input 3. You mean when we get the context of this condition, how to do we need to also include here, right?
It seems like we don't want to include the third one, but
Yep.
it seems like that's what would happen if you concatenate them all next to each other.
So you need to do something before this concatenation.
Okay.
Or yeah, that's actually so you can.
I think all the MFCCs are 15 dimensional, and what you're talking about is of audio recording. Audio recordings are of different lengths, but one MFCC has 15 dimensions, and you
But
go
if
through
you,
the
if you look
audio
at,
recording.
if you look at that line there, it says that each MFCC is of length t by 15. Of varying lengths t. Like that's what's being called MFCC in the code right now. So it sounds like we should find some way so that when you take the last element from one of them, you pad it instead of going into the next one.
So I think that could be done like through by using the collect function, right?
I think I'm not sure, but I think this might be like there might be a typo here or something. But as much as I remember, we have audio recordings. Each MFCC is a 15-dimensional array. Is it not right, Rayu?
Agreed it's 15 dimensional, but doesn't it have another axis, the time axis?
Oh yeah,
So
yeah.
That's the one that's being concatenated along. Okay, I know what I think should happen. I'm curious if it's matching what is here.
So maybe maybe we can like discuss that later.
Yep.
Okay. So for the parameter configuration, these things we listed here are just the like very basic configuration of the model and the training. So the number of epochs here is the number of epochs that you want to iterate over the whole data set, the training set. Batch size is the like the number of examples you want to pass in each backward propagation or the parameter update. You can feel free to add any other parameters here in the config. So here you just need to use the data set you implemented before, and then read and then generate the 3 data sets yourself, and pass these data sets into the data loader provided by PyTorch. So you could just enumerate over the data sets at training time, or the inference or the prediction time. So for the model architecture, you need to implement this NN.module class, and the count. So you can define the arguments you want to related to your model. So here we define the context size, and the input size should be a one-dimensional. The input should be a one-dimensional vector because we are using the fully connected network, which could only take one-dimensional input. So think about how to convert the the 2 times context size plus 1, 15 vector, that 2-dimensional vector, to a first dimensional vector in your data set. And the output size is 40. So the reason behind it is it's related to the number of labels that you want to predict. So you don't need to predict the SOS and UOS, and you need to predict all other labels. So in your last output layer, you will let the model predict the probability of each label, and you're going to pick the highest one as your output. For the like the model part, we are defining just a single linear layer for you without any activation functions or just fancy things or like stacking them together. This one will allow you to cross the very low cutoff. So you could come back to this model part later when after or optimize the architecture after you make the other submission. I think this part is just like defining the loss criterion, the optimizer, and you might want to use the learning rate scheduler to adjust the learning rate automatically. We found this useful under like most of our homework. So please make sure to read some documentation of these learning rate scheduler. And of course, you could change the optimizer yourself. You can use AtomW, autograd, those kind of things. So that's up to you. But remember that in our homework 1.2, our total parameter size is limited to 20 million. So after you run the summary, you can get a like the parameter size information, and you need to make sure that that number is lower than 20 million. For the training part, you just pass the input to your model and then get the output, and use the criterion function you defined earlier, and use it to calculate the loss, and then like do the backward propagation, and update the model parameter. For the evaluation, this time you don't want the model to update you don't want the model to update the parameter inside. So you need to set it under the evaluation mode, and make MyTorch aware of the inference happening right now. Let's see. So here you don't want you don't need to do like all the previous part, the loss backward propagation, the optimizer step, those things. You just need to get the prediction of your model, and then calculate the things you want to see, calculate the performance matrices you want to see in the evaluation mode, like the accuracy here. This is the WMB setup. If you want to use it, just follow our previous presentation. For the this is the final training code. You want to iterate over the training set for the non-epochs time. So you need to create a for loops, and then for each run, you train the whole data. You train on the whole the input the training set, sorry, and then run the evaluation function to get the accuracy after you train, like after you finish the training on this epoch, and then you can choose to only save the best model based on the accuracy information reported by the evaluation set, by the evaluation function. So this part is the model saving part. And for the testing, here you don't need to get the label from your dataset because you don't have that information. So you just need to get the input from your test loader and then use your model to make the prediction and save it to your output. And for the output here, you might want to do some, you might want to convert it to CSV file. I'm so sorry, to the pandas data frame, and then use the pandas dot to CSV function to store it. Or you can also use the code here to write the predictions into the submission CSV file. And for the submission, this is the command to use the Kaggle API to submit. But you could also save the submission file yourself and then go to the web page and submit it manually. Yep. I think this is a walkthrough of our Starter notebook. Is there any questions?
Yeah, can you upload the recorded file on Piazza
Yeah.
or wherever?
You mean the recording of the this bootcamp?
Bootcamp, yes.
Okay. Yeah, we will upload that later.
Does part 1 have any bearing on part 2? Do we use MyTorch in part 2 at all?
So part 1 and part 2 are totally separated. So in part 1, you cannot use anything related to PyTorch. You are implementing PyTorch using the NumPy things by yourself. But in part 2, we expect you to use the PyTorch function directly. So they're not related.
For part 1, it tells us we have to use specific versions of certain libraries. Do we also get that for part 2?
I don't think so. You can
think
use
so.
the latest version of PyTorch, because we will be needing your CSV files that you can generate with whichever version.
Yep. So if you use the Colab to train your part 2 model, I think all the things you need to do about the version is just this command to upgrade the Kaggle API, and you can use the default PyTorch on your Colab machine. Okay, if there is no more question, then thank you for coming to our bootcamp. And yeah, that's all.
Thank you.
Thank you.